Hey, good morning, Year 12s. We're going to start. Today we'll be looking at 225 in your notes, which is the manufacture of iron. But before that, we're going to just quickly go through the homework. Now, I have posted the answers to the homework on Google Classroom anyway, so I'm going to go very quickly, but if you miss anything, you can just check the answers yourselves, okay? And due to the joys of Google Classroom, I know who hasn't done their homework, so I'm recording all that. Okay, so metal used for galvanizing is zinc. Chemical name for rust. Now you learn this, they ask this a lot, and it's usually a 2-marker. It's hydrated iron 3 oxide. You must include the 3. If you left that out, you'd only get 1 mark. Okay, so just make sure you're very accurate with that. Okay, this one here, and then the answer to 9, it's that magnesium is more reactive or higher in the reactivity series than iron. So it reacts or corrodes reference to iron. Don't say rust. Rusting only applies to iron and ferrous materials such as steel. Okay, so we have questions then. So explain how covering an iron strip, it forms a barrier, right? So that's the barrier method, forms a barrier between the iron and the oxygen and water, so to prevent reaction, or rusting, whatever, if you want to put that there. Just remember to always name the substances that cause rusting. Both of those are required. Painted cars, paint forms a barrier between the iron and the oxygen, which I spelled wrong. Prevents and water, so prevent reaction, 31. Zinc blocks. Copper would be ineffective because it is lower in the reactivity series or less reactive than iron, so will not react. So iron will react in preference to copper, or copper will not react in preference to iron. Sacrificial. There's a number of answers here. A more reactive, I would just define what sacrificial protection is. It's that a more reactive metal corrodes in preference to iron, so to sacrifice to protect the iron. And then you have these test tubes. Now I changed just so you could see kind of maybe how you might deal with data here. The nail masses they're not all the same. Okay, so that you could have said when it asked about a fair test, you could have the same mass of nail, certainly the same surface area of nail. So in order to allow for that, you can obviously calculate the change in mass, right, by just subtracting the initial from the final mass. That's easy enough. Okay, and always you've got here, everything here is to 2 decimal places, so it's good to always record 2 decimal places, even if that's 0, right? That's actually a thing at A level. They might judge that at GCSE, so just always record the correct number of decimal places, even if it's zeros. Now, and then a better way to compare masses is the percentage change in mass. Okay, so if you wanted to calculate that, it's the change in mass divided by the original mass, and then times your answer by 100. Okay, but either way, you could see that obviously, whatever way you compared it, test tube 1 had a greater increase in mass than test tube 5. Right, so they had all of the diagrams. Which nail increased most in mass? It was 1. Which nail least increase in mass? That was actually a bit confusing. I thought, looking at it again, right, there's 4 of them that didn't increase at all. So my initial thought was to list all those, but you could have said nail 5, which had an increase in mass, but it was less. Explain why the increase in mass. The reason is rusting. It occurred. Iron becomes hydrated iron 3 oxide. Check that now. That's probably a mistake in the one I sent you as well. Which has a greater mass than iron, I should have said. If you remember from last year, the RFMs, adding together the mass numbers to get the mass of any substance. Explain why nail 2, right? Because there is no water. So remember, if you're missing either water or oxygen or both, there will be no rusting. The scratch increased the rate of rusting in test tube 5. It occurred. We know, I don't know why is that a mistake? We know because there was an increase in mass compared to test tube 4. Now I'm giving quite detailed answers, which I'd encourage you to do when you're sitting exams. Give as much detail as you can. Don't leave it, just don't write short answers. Just because you know in your head what you mean, you have to show the examiner what you mean. Okay, other variables you could control. I think I'd said to a few of you the time, but actually having a look back on it, they'd already said everything was left for 6 days, so the time was already controlled variable. The mass and or surface area of the nail, and definitely the temperature. Temperature is always what you want to go for controlled assessments, because if you increase the temperature, you're going to increase the rate of any chemical reaction. We'll do that hopefully later in the year. right? Reactant to boil water contains no oxygen. Oil prevents oxygen dissolving from the air when the water starts to cool. Okay. And how is iron best protected against rusting? Again, this was a bit vague. I thought, best protected, I suppose you're going to go for the sacrificial protection option. You could say by galvanizing or by sacrificial protection, or you could describe sacrificial protection. So which is using a more reactive metal in contact with iron that will corrode in preference to it. Okay, zinc. Right, so the answer was zinc, and why zinc is more reactive than iron, so it will react in preference to it. Can I just really emphasize that this is a bog standard answer to explain sacrificial protection, right, why it works. Okay, give an example of a metal that could not be used to galvanize, so anything below iron in the reactivity series cannot be used. And why did the scratch the nail? So that's the joy of sacrificial protection, is you don't need to coat the entire material in the more reactive metal, it just has to be in contact with it. So even if you have a scratch or a break anywhere and the iron is exposed, it will still not rust. Okay, so we're going on now to, so as I say, you can check those answers yourselves. They're all on the classroom if you want to go back and check anything that's on there. Right, describe, this is the most difficult part, I think, of this. Describe the extraction of iron from hematite, because there are 5 chemical equations. There's a number of processes going on. So the way we're going to handle it, right, is not just, we're going to use the notes really to form a graphic organizer on this. Now you can have a look, you're going to need your notes handy for this next bit, okay? There's a very detailed diagram here, okay, which you will need to know all of the bits of, but we're going to take it bit by bit. And then I've listed the chemical processes. So it's actually, if you look at it, it's not a lot of information, but it is just how you structure it in your head, how you get it into your head is the difficult part. Okay, so have a quick look at this diagram, right? If you have, I'm going to just show you the revision book version of this. If you want to use it, it's up to you. Find it. Okay, so it's on, I've sent you the revision book chapter, I'm pretty sure. Okay, so it's in there as well. And again, similar to the layout I have in my notes. That's not a coincidence. Okay, so right, so let's have a look at how we're going to structure this. Now, the first thing I want you to do, right, so have your notes open at the page with all the information about this. And I want you to copy out this graphic organizer. And I'm going to show it to you now, if I can. No. Okay, found it. Okay, so you can see, right? So I want you to get, now there are A3 sheets in, they're either in the first or second, you know, the long drawers just under where my kettle is, right? Near the prep room door. So if you're allowed, Mrs. Carter doesn't mind, you can get yourselves an A3 sheet, a blank A3 sheet, and you can copy out this graphic organizer. Okay, so maybe Mrs. Carter could pause the video at this point, or you can pause it yourselves, depending on how you're looking at it, and just copy this out, and as I say, leave plenty of space between every. So I'm going to keep talking, so you need to pause the video at this point to have time to copy this out. All right. Okay, so I'll assume you've done that and you're back. Now, if you look at the top row here, these 5 substances, right, are all the substances that go into the blast furnace. Now, if you look at the diagram at the top, what you put in at the very top, like, so the blast furnace is like a big chimney, really, it's just that. I mean, obviously fancy stuff happens in it, but ultimately it's just a big chimney. Okay, so what you've got here is you put in coke, right, hematite, which is your iron ore. I'm just going to try and use different pens. Okay, so I'm going to actually keep that as purple, because you don't really want, you want to know that hematite is the iron ore. Don't use the term iron ore at the top. So the ore is just a rock that contains enough iron to make it economically worthwhile to extract, right? It's just a rock made with Now, and the particular type of rock is called hematite. Okay, there are others like magnetite and that. So hematite is a particular type of iron ore, the particular type of rock that you're using. Okay, now hematite is contaminated with, I'll maybe put this in green. Hematite, it has an impurity, right? It contains an impurity. Okay, and that impurity is sand, right? So you don't want that. This is everything. Every rock has sand in it, silicon dioxide, okay? So it's just something you have to get rid of. Okay, and you're also adding limestone in at the top. So the three solids you're adding in are limestone, hematite, and coke. And then at the very bottom of the blast furnace, you're blasting in hot air. Now it's called blast furnace because of this. You know, back in the old days, they had these kind of bellows that looked like accordions, you know, and they'd actually squeeze them and push air in, right? And that's to obviously keep the combustion reactions going, and other ones, as we'll see. Okay, so the first thing we're going to do is, they're the common names of everything. We're going to put in their chemical names, right? So I'm going to use blue pen, but you can just use the same color pen. But if you can, use different color pens for everything, just so you know what's connected to what. Okay, so again, I want you to pause for a moment. I'm just going to do the first one. So hematite, the chemical that's in hematite is iron 3 oxide. Okay, so that's the chemical that's in it. Now I want you to pause at this point, look at your notes, and find the chemical name of the other 4 substances along the top here. So hopefully you can pause, or Ms. Carter can pause for you, and you can check this. So what you should have got is limestone is calcium carbonate. Sand is silicon dioxide. You won't have heard it much, but it's everywhere, right? Hot air, the important chemical in it is oxygen. And coke, the important chemical in it is carbon. I'm just going to move this over a wee bit. Okay, and then we're going to put in the chemical formulas as well. So if you could pause for another moment and find the chemical formulas for each of those. So this is, I'll try and bring it down a wee bit. So this is CaCO3. This is SiO2. Over. This is Fe2O3. This is O2. And this is just C. Okay, so there's the chemical names and chemical formulas of all the substances you're adding in to your blast furnace, right? So now, there are 2 processes going on. We're going to deal with individually. If you look at the graphic organizer, okay, and I have something, a light shining somewhere. I'm going to try and get rid of that. Right, have a look at that graphic organizer, and you'll see that there are 2 substances produced. There's slag and iron, right? So there are 2 products. Two products from the blast furnace. Okay, there's slag and iron, and 2 different sets of reactions to produce each. Okay, so we're going to look at, and if you look at the diagram of the blast furnace, so I'll put back up. Okay, that's the one from my notes. If you look at the diagram of the blast furnace, you'll see that at the bottom you get molten slag. Now that means it's a liquid, right, because of the temperatures involved. Molten slag, and it's less dense than the iron, so it actually floats on top of it. You get molten iron, and then you just tap them out at different points. Okay, so they're the 2 products produced. Now we're going to look at how I can get this back. I'll actually share that. Okay, so we're going to look at the manufacture of iron first, and I'm just going to move that to one side so I can zoom in on this a wee bit more. Okay, so the connecting purple lines in each case generally, well, they're to indicate some kind of maybe a chemical reaction between them. Okay, so let's start with the actual first thing that happens here is the reaction between the hot air and the coke. Now that's carbon and oxygen. Really, you have a combustion reaction, right? So the first thing that happens, I'm going to put this in black, right? First chemical reaction that happens is that you've hot air and coke combined to give carbon dioxide, right? So these two react together. Okay, so you put that on the arrow. So the two of those react together and they form carbon dioxide. So we're going to have to do a word equation for that. We're going to do word equations first. But if you look at your notes, you should find the word equation for this. But it's a so we're going to call this equation 1. So carbon, I'll have to go over here. Carbon plus, no, I need more space. Carbon plus oxygen, arrow carbon dioxide. Okay, and I'm going to try and leave room for the chemical equation. Right, and then the second reaction that happens, right, so this time it actually happens that more, what next happens? Actually, more coke and carbon dioxide combine. So actually, should we have hot air and carbon dioxide at all? No, they don't actually meet. Actually, the coke and carbon dioxide. So just sorry about that, guys. I think I copied this from somebody else and theirs isn't quite clear. Right, so in this instance, the second reaction is that these, let's see, coke reacts with carbon dioxide. So the first thing is they react together. The second thing is these react together. And you get a second chemical reaction, which is carbon dioxide plus carbon, arrow carbon monoxide. Okay, so that's the second process. So there's actually, now the carbon monoxide is key, right? It's formed within the blast furnace. Now it is the reducing agent. Now a reducing agent, right, this is the redox topic, so this is all going to come up again. The reducing agent, it causes reduction. Now, who can remember what reduction is and not make mistakes like I do? So reduction is loss of oxygen and or gain of hydrogen and always gain of electrons. So the third process that happens, right, is that the hematite and carbon monoxide react together. So once the carbon monoxide gas is formed inside the blast furnace, it meets, remember this is just a type of rock, probably melted at this stage. So this will be bubbling through, it'll meet some of the hematite rock and it's going to reduce it, right? It's going to cause it to lose oxygen. So what happens is the iron 3 ox, so this is the third process. Let's put it over here. No, I'll put it here. Right, the third reaction is that iron 3 oxides and carbon monoxide combine, react together, and you get iron and carbon dioxide. So there's a lot of carbon dioxide produced in this reaction, right? You've got to produce twice. You've got to produce when the coke and hot air react together, and you've got to produce when the carbon monoxide and the iron 3 oxide react together. Okay, so we're going to discuss this briefly because this all comes up with the redox. Now, let's have a look. What pen haven't we used much of? Okay, what have we still left to do? Okay, so we still have to put in chemical formulas of carbon dioxide, carbon monoxide, and iron. Okay, so carbon dioxide is CO2. Carbon monoxide is CO, and iron is Fe. Okay, so just to keep everything right. Now, I'm going to leave chemical equations, the balanced chemical equations, to the end, because you know that I'm encouraging you really to make sure that you get the word equations sorted and understand those, and then the balanced chemical equations might come together before the end of the year if you work on them. Okay, so first thing, but we are going to identify oxidation and reduction here, right? So you might need your notes for help with this. I'm going to use, what haven't I used yet? Red. Now, have a look at carbon plus oxygen giving you carbon dioxide. Can you see any redox process there, any oxidation or reduction? Oh, look, carbon's gaining oxygen, right? And what is gain of oxygen? Oxidation. Okay, so carbon is oxidized. So this is a very straightforward, obvious oxidation process, right? Carbon gains oxygen, gain of oxygen is oxidation. Okay, let's have a look here. Carbon dioxide plus carbon gives you carbon monoxide. Now it's the CO2 and that's the CO. So that seems to have lost oxygen, right? So this losing oxygen is, remind me, reduction. So carbon dioxide is going to be reduced. Okay, so you've got reduction of CO2 here. But look, what has happened to the carbon? Has anything? It's also become carbon monoxide. It appears to have gained oxygen. Right, so this is actually oxidation of carbon. And what is a reaction in which you have both oxidation and reduction? A redox reaction. So that's a really obvious redox reaction, okay? Now, what about down here? I think we might have seen this one before, because I know I put it in the notes somewhere. Right, so again, we have oxidation and reduction. I want you to just pause maybe for a moment and have a think. Can you identify both oxidation and reduction? And remember, you're looking at what happens to the reactants here, and the change in oxygen content is the easiest thing to look at here. Okay, so iron 3 oxide loses oxygen. So it must be reduced. The carbon monoxide, right, you can see it's formed here and it's being regenerated here. So it's just, it kind of doesn't change overall. It's just kind of a carrying, an oxygen carrier, right? So carbon monoxide has gained oxygen. It's gone from carbon CO to CO2, and then it has been oxidized. So you've oxidation of, I'm sorry for mixing up my capitals and smalls, bad habits, oxidation of carbon monoxide. And you know, because it has gained oxygen. Okay, so that is how we get the iron, right? We react, we burn this coke, right, which is carbon, right? And I know there's always a joke about why it's called coke. It's a very boring reason. Coke is just a merge of the words coal and cake. I don't know why they call it cake, but it was just a way of getting coal that burned hotter, right? So coke, the carbon, right, coke and the hot air and the carbon and oxygen in them react together to form carbon dioxide. That's inside the blast furnace. Then that meets more coke, right? There's lots of it there. And when it meets the coke, it reacts with it to form carbon monoxide. And this is the reducing agent, right? It causes reduction of the iron 3 oxide in the hematite. And that will produce iron as a molten right, material. And so if it's a molten, we would give it the state symbol L. It's going to be liquid iron coming out of the bottom, just because it's above, the whole thing is hot, about 1500 degrees C, higher than the melting point of iron, right? Okay, so that's the first process. Now, what's happening over here? There's a second product formed, right? Now, the sand is an impurity, so if you just left it there, did nothing with it, it would contaminate your iron, right? You would have really rough iron mixed in with this silicon dioxide, real crumbly and useless. Okay, so they discovered, way before they knew the chemistry, lucky them, they discovered that if you put in some limestone, right, into the blast furnace with the hematite and the coke and the blast of hot air, you would remove the sand, okay? Now, the sand is an acidic impurity. So there's a mention, if you look at the specification, it talks about the acidic impurity. Just be very clear that that's the sand, right? This is the acidic impurity. Now, I think if we ever get to do the last topic in this, you'll find that all non-metal oxides are acidic and all metal oxides are basic. We've seen that before, that magnesium oxide and so on act as bases. That was last year in the acids, bases and salts topic. It just happens that anything like silicon dioxide, carbon dioxide, sulfur dioxide, any non-metal oxides are acidic. Okay, they react with bases. Okay, so this is, just be very clear, because so the sand, silicon dioxide, is the acidic impurity and needs to be removed. Now, how it's removed is with the limestone, and not directly. Limestone will not react directly with silicon dioxide. But if you heat the limestone, right, what are we using? So this is the fourth reaction, right? This is a thermal decomposition. In other words, if you take the limestone, the CaCO3, and you heat it up hot enough, it'll actually break down into two different substances. One of them being calcium oxide and the other one being carbon dioxide. So I'm just going to put the chemical equation over here. So calcium carbonate. Actually, I'm going to just move it. If you just heat it, well, a lot, right, you get calcium oxide, which is a base because it's a metal oxide. And you also get yet more carbon dioxide. Okay, so we've got a third process producing carbon dioxide. This is not good for the environment at all. Actually, this process of producing iron is done on such a large scale that it has been a major contributor to greenhouse gases. Right, but anyway, that's for environmental technology. If anybody does it here. Okay, so so this is the chemical equation, or the word equation for that. So now you've got this calcium oxide. Now it's a base, and voila, we have acids. So if we react an acid and base together, we're going to get what you could classify as a salt. Okay, so we have got, now what you produce with the two of those is you get slag. Right, slag is just, it was an old-fashioned name, and as I say, they were able to extract iron from hematite from as the Iron Age, was that thousands of years before BC, for common, whatever they call it now, for Christ, for common era. So obviously back in the day they didn't have to suffer the knowledge of all this, but so slag was just a name they used for waste product. They just chuck it into big hills. Okay, now it's used as road to sort of filler for roads and so on. Okay, so slag, it's got a fancy chemical name, if you can find, right? It's called calcium silicate. Now, if you think about it, in the name, even though it sounds a bit strange, it's obvious it has three different elements present. It has calcium, silicon, and remember the ATE ending always means you've got oxygen as well. Now, its chemical formula is CaCO. That's how a lot of people remember it, with a 3 at the end. So it's CaSiO, and then there's 3 oxygens. Okay? You pretty much need to learn that. Now, the chemical reaction that gives you that. So this is, if you like, this is our fifth and final reaction. So it's an acid-base reaction. Or neutralization. Nah, I'm reluctant to call it that. I mean, it is. You could call it neutralization. So what you have is calcium oxide plus silicon dioxide, and that will give you, I'm not going to be able to put it on, calcium silicate. And that's the end of that, okay? Now, I haven't put in the chemical equations, right? I'm just going to list them downside very quickly. So the first one is carbon plus oxygen, giving you carbon dioxide. Don't need to balance that. The second one is carbon dioxide plus carbon, giving you carbon monoxide. I do need to balance that because I've got two carbons on the left and only one on the right, two oxygens here, so I end up with two carbon monoxides. The third equation is our hematite, which is Fe2O3, reacting with the carbon monoxide reducing agent, giving you iron, molten iron plus carbon dioxide. And now this balancing, I would just learn this off, right? You have two of those. Now you need a carbon monoxide for every oxygen here, so you're going to need three carbon monoxides and you're going to get three carbon dioxide. The fourth, now that's our manufacture of iron, so I kind of consider those as one set because iron is produced at the end. And then our fourth and fifth are the removal of acidic impurities bits. So the first one is the thermal decomposition of calcium carbonate, calcium oxide plus carbon dioxide, that doesn't need balance. And finally, the calcium oxide and silicon dioxide. And you basically just add them together, you get one substance, CaSi, and 2, 3, three oxygens, right? And that's your slag production, right? So removal of acidic impurities. Okay, that's it. Now to do is questions on page, where's my notes? Okay, so we've had a look at this, right? So flick through it. Chemical processes, right? So all there, and I want you to try all of the questions on page 11 now, please. And have I mentioned there's a test tomorrow? There's a test on metals, the metal topic tomorrow. Can I just ask you very much to concentrate on the main reaction? I'll maybe do that in a little second video. Okay. And last bit, just to finish it off, it just says here, 226, demonstrate knowledge and understanding that iron is used in bridges and structures due to its strength. Okay, so you just need to know that it's used in bridges and structures, right? You can be examined on that. I'd also like you to do the questions at the top of page 64, page 12. There is just a couple of questions, one question, just on that 226. Okay, thank you.